Another key property of waves is called phase, and here we're going to look at how we can measure the phase of a wave and the phase difference between two waves. So here we've got a sketch of a wave, and we can see we've got the typical sinusoidal wave coming up and down, up and down. These axes can be whatever you want for the purposes of this explanation, so displacement against time or displacement against position. And we can see that the wave is formed up of this repeating cycle. So if we were to start here, by the time we get to here we've completed one cycle. By the time we get to here we've completed another cycle, and here another. So as we come along we're going through this cyclical repeating motion. And the phase of a wave is a way to describe where along here we are looking, so where in the cycle we are looking at on a particular wave. So we've said before we might measure the displacement at a particular time or a particular position, but we could also say what's the displacement at the particular phase. And the way we do this is we start off by drawing an analogy with a circle. So in a circle, if we were to imagine going round and round in a circle, then as we do so we're going in a repeating motion. Just as we go through the cycle we go through a repeating motion. So this point up here might correspond to the start of the motion. As we come around here, when we get to the halfway around the circle, that would be this point, and then back around to the start of the next cycle is when we finish coming around the circle and we're back up here. And so we measure the phase in a wave as an angle. So we could see that if this was the center, this might be 0 degrees out here, so up here would be 90 degrees, down here would be 180, 270 and 360 when we get back to the start. But rather than measuring it in degrees from 0 to 60, the preferred method of measuring angle is in radians. So we start from 0 radians and we go up to 2 pi radians. So this would be pi by 2 radians, halfway along would be pi radians, 3/4 is 3 pi by 2 radians. So we can label the phase on this using this. So this would be 2 pi phase, this would be the 3 pi by 2, this is the pi radians, and here we've got the pi by 2 radians with the 0 of course here. So we don't have to take the 0 at this point in the wave. If we wanted we could have taken this peak as the start of the wave. This would be 0, pi by 2, pi, 3 pi by 2 and 2 pi up here. So we pick our own arbitrary start of the wave, and then we use this phase as a way to describe where in the wave we are. So somewhere along here we might be 1/4 of a pi phase. So we can use the phase to describe where we are in a wave, so at what point we are in a wave. But it becomes more useful once we've got two waves which we compare. So here we've still got the blue wave, but I've added on a second red wave. And if this was the displacement against time, then this second red wave has exactly the same amplitude, it's got exactly the same period, same frequency. If this was displacement against position it would have exactly the same wavelength, but clearly these two waves are not exactly the same. They're kind of offset from each other. And so this phase is how we can describe the difference. We would describe a phase difference between these two waves. So we would say, if we are at some point in this wave, where are we at in, what point in the phase are we in the other wave? So if we go from here to here, we would label this, let's switch to the blue to be nice and consistent. So this might be our naught, this would be our pi by 2, here's our pi phase, here's the 2 pi, and the 3 pi by 2 down here. Now we can do the same thing on the red wave. We can label up equivalent points on the red wave. So the equivalent 0 point on the red wave would be here. We'd have the pi/2 here. Here's pi. Here's 3 pi/2. And here's the 2 pi back to the start of the next cycle. And so we can see where the blue wave is at 0 phase, the red wave is at pi/2 phase, where the blue wave is at pi, the red wave is at 3 pi/2. And so we can describe this offsetting between these two waves as a phase difference. What's the difference in phase at any given point? And so we can see that throughout this we've got a difference of pi/2 in the phase. So at any point the red wave is to the left of the blue wave by pi/2. So if these waves were travelling to the left, then the red wave would be said to be leading the blue wave by pi/2. If these waves were travelling to the right, then the red wave would be said to be trailing the blue wave by pi/2 radians of phase. So that's essentially the concept. It's just a way of labelling where we are in the cycle, which then allows us to compare two waves which are almost identical but just slightly offset. We could, if we wanted, on this time axis, describe this as a time offset. So this might be the red wave leads by 1 second, or if this was a position axis, then we could say the red wave leads or trails by 1 meter. But it turns out in the long run that using this phase difference to measure it becomes a bit more useful, a bit more insightful. And we'll cover that when we get onto the likes of superposition.